Good afternoon. My name is Ryan Donlon, and today is February 23rd, 2026. This presentation examines the relationship between artificial intelligence, AI, decision support systems, DSS, and expert systems, ES, and how these technologies collectively enhance organizational decision-making. The purpose of this briefing is to synthesize the concepts covered this week, including machine learning, predictive analytics, ethical considerations, and implementation best practices. As AI continues to influence enterprise operations, understanding how these systems function and how they should be governed is critical for responsible and effective leadership. Artificial intelligence serves as the foundational capability that enables intelligent decision-making systems. Within this broader field, decision support systems and expert systems represent applied tools that help organizations analyze information and guide complex decisions. This topic was selected because decision-making lies at the core of organizational success. In modern enterprises, decisions must be data-driven, timely, and strategically aligned. Understanding how AI enhances or constrains decision-making provides leaders with the knowledge necessary to deploy these systems responsibly and effectively. The integration of AI into decision processes has significant operational, ethical, and strategic implications that warrant careful examination. Artificial intelligence is defined as the study and development of intelligent agents capable of perceiving their environment and taking actions to maximize desired outcomes. Decision support systems are computer-based systems designed to assist in organizational decision-making by analyzing data and presenting actionable insights. Expert systems, by contrast, simulate the reasoning of human specialists by applying rule-based logic within a specific domain. The relationship among these technologies is hierarchical. AI provides the computational and analytical foundation. DSS applies AI techniques such as machine learning and predictive modeling to assist decision makers. Expert systems encode domain expertise into structured rules to replicate expert reasoning. Together, these systems enhance analytical capability while still requiring human oversight and accountability. Decision support systems can be categorized into model-driven, data-driven, and knowledge-driven systems. Model-driven DSS rely on statistical and mathematical models to generate recommendations. Data-driven DSS analyze large datasets to uncover patterns and trends. Knowledge-driven DSS incorporate expert rules and structured logic to guide decisions. The primary value of DSS lies in improved accuracy, efficiency, and consistency in decision-making. By processing vast amounts of structured and unstructured data, DSS reduces cognitive overload for decision makers and enhances strategic insight. However, the effectiveness of DSS depends heavily on data quality, system design, and appropriate interpretation by human stakeholders. Expert systems are designed to replicate the decision-making processes of human experts with specific domains. These systems typically consist of a knowledge base, a rule set, and an inference engine that applies logical reasoning to a given problem. One advantage of expert systems is explainability, as rule-based reasoning can often be traced and reviewed. However, these systems are inherently limited by their scope and the quality of the encoded knowledge. They lack contextual awareness and adaptive judgment beyond their program rules. As a result, while expert systems improve consistency and scalability of expertise, they do not replace the need for human supervision and domain expertise. Machine learning is a subset of AI that enables systems to learn patterns from data and improve performance over time without explicit reprogramming. Supervised learning techniques such as linear regression and logistic regression are commonly used in predictive analytics to forecast outcomes or classify events. Unsupervised learning identifies hidden structures within data, such as clustering and anomaly detection. Reinforcement learning optimizes decisions through feedback from environmental interactions. The integration of machine learning into DSS significantly enhances predictive capability and automation. However, reliance on algorithms introduces risks related to data bias, overfitting, and model drift. Therefore, continuous monitoring and validation are essential to ensure reliability and fairness in AI-enabled decision systems. The expansion of AI-driven decision systems raises significant ethical concerns. Bias may be introduced through unrepresentative data, flawed algorithm design, or systemic inequalities embedded within training datasets. Transparency is often limited in complex machine learning models, reducing explainability and stakeholder trust. Additionally, questions of accountability arise when automated systems influence high-stakes decisions. Floridi and Tadeo, 2018, emphasized that data ethics concerns the moral implications of data collection, processing, and usage. To mitigate ethical risks, organizations must implement governance mechanisms, conduct bias testing, ensure transparency in decision logic, and establish clear accountability structures. Responsible AI implementation requires both technical controls and ethical leadership. Effective implementation of AI in decision support systems requires a structured and iterative lifecycle. Organizations must begin with clear problem identification and stakeholder engagement. Data collection and reprocessing must prioritize accuracy, relevance, and fairness. Rigorous evaluation and validation techniques should be applied before deployment. Once deployed, continuous monitoring, auditing, and maintenance are essential to detect performance degradation or unintended consequences. Involving domain experts throughout the lifecycle strengthens reliability and contextual alignment. Successful AI systems are not static. They require governance, adaptability, and sustained oversight to remain effective and ethical. Real-world case studies illustrate both the potential and the risks of AI-enabled decision systems. Amazon's recommendation engine demonstrates successful integration of machine learning into decision support, improving personalization and customer engagement. In contrast, Microsoft's Tay chatbot illustrates how insufficient safeguards and oversight can lead to harmful and reputationally damaging outcomes. These contrasting cases underscore the importance of governance, bias mitigation, and monitoring. AI systems influence real-world behavior and outcomes. Therefore, responsible design and oversight are critical components of organizational leadership. In conclusion, artificial intelligence provides the foundational capability for advanced decision-making systems. Decision support systems and expert systems operationalize AI within organizational contexts, enhancing efficiency, scalability, and predictive power. However, these benefits are accompanied by significant ethical and governance challenges. Organizations must recognize that AI does not eliminate responsibility. Rather, it implies the consequences of design choices. Effective leadership requires balancing innovation with accountability, ensuring that AI-enabled decisions are transparent, fair, and aligned with organizational values. When properly designed and governed, AI-driven decision systems can significantly enhance strategic performance while maintaining ethical integrity.